Here's a smartphone, and whenever you take a picture, receive a message, or download an app, it saves that data into this gray, rectangular, and overall rather boring-looking microchip. But this memory storage microchip is far from mundane, because the level of technology inside it will astound you. To begin, let's open this microchip and investigate. First, we see that this one component holds a stack of 8 chiplets. Let's zoom in further to a nanoscopic view of one of these chiplets, and in it we find a massive array of memory cells stacked 100 layers tall by 40,000 columns wide and 50,000 rows down. These memory cells are called charge trap flash, and each memory cell contains a charge trap in which different levels of electrons are used to store 3 bits of information. But here's the issue. How do scientists and engineers design billions of nanoscopic memory cells that can reliably trap electrons for years on end? This is crucial because if the electrons are not properly trapped, your saved pictures and files would become corrupt, and you would lose entire sections of data. To solve this and prevent electrons from leaking out, scientists and engineers surrounded the charge trap with dielectric materials, which are non-conductive insulators that stop electrons from passing through. You can think of this charge trap as a valley, and the insulating dielectric as the walls of the valley. And when electrons are moved onto the charge trap, they become trapped in the valley with no way out, and they can stay there for years on end. This is the basic idea of how your smartphone stores its information. However, this setup poses a new issue. You see, the channel where the electrons come from is over here on the other side of the dielectric barrier in a valley of its own. Now we have 2 valleys with a rather high barrier in the middle. Electrons can now comfortably stay in one valley or the other. But here's the problem. How do we move the electrons we want from the channel across the dielectric and into the charge trap valley? Or, in other words, how do we write information to a memory cell? Well, that's where quantum mechanics comes into play. In classical mechanics, this electron is a localized point charge with an energy level. The dielectric is an electrical insulator, and the minimum energy level required for electrons to get over the barrier is so high that doing so would take a lot of energy, which would damage the barrier itself. And thus the electron can't pass over the dielectric. However, in quantum mechanics, the electron's location is not a point, but rather it's a probability density, or a cloud, that depicts where the electron is most likely to be found. When we apply a positive voltage on the gate over here, the positive electric field attracts the negatively charged electron's probability cloud from the channel and pulls it towards the charge trap valley. If the dielectric barrier is thin enough and the pull from the positive voltage on the gate is strong enough, then the electron's probability cloud is pulled far enough across the dielectric barrier so that there becomes a sizable probability that the electron will find itself on the other side of the dielectric barrier and into the charge trap. This phenomenon is called quantum tunneling, since it can be imagined that the electron tunnels through the barrier instead of going over it. And every time you take a picture, your smartphone uses this phenomenon to write information to the charge trap flash memory cells. Scientists and engineers use a set of quantum mechanical equations developed by Ralph Fowler and Lothar Nordheim in the 1920s for figuring out exactly how thin the dielectric barrier should be and how strong the gate voltage should be in order to tunnel electrons from the channel across the dielectric and into the charge trap. In fact, perhaps the most impressive detail is how thin the dielectric barrier is. These are some of the smallest things humans have ever mass-manufactured, and, as you see, the dimensions shown here are in nanometers. If we were to zoom in on the dielectric, we find that it's only 75 to 100 atoms thick. The dielectric walls can't be thicker, because if they were, the required voltage would be considerably higher, and the extra voltage would cause damage to the memory cells. And if the walls were thinner, there would be a higher chance that the electrons would leak out. It's amazing that these structures are found in billions of identical charge-trap flash memory cells in your smartphone, and in every smartphone in the world. Of course, to save a picture onto your phone, you don't have to understand quantum mechanics, but it's interesting to know that it's happening.